Welcome back to another AP Physics 1 topic overview. Today we're going to be talking about projectile motion. So let's get right into it. Alright, so for any of the facts that I go over today, the fact sheet will be in the description down below, along with a link to the examples. So the first facts we're going to go over here is what exactly is projectile motion. We have to do with free fall, but now we have also the object moving horizontally, not just vertically. So vertical acceleration, we know this already from just regular one-dimensional free fall. That's 10 meters per second, meaning that I'm going to gain or lose 10 meters per second of speed each second. Horizontal acceleration is always 0. We'll talk more about that when we draw our free body diagram for the object in the air. Then we have velocities in perpendicular directions add just like perpendicular forces. That's going to be our x and y components. Talk more about that in a second. Magnitude of the object's velocity is known as its speed, such as means velocity without direction. And then when we do our projectile problems, we're going to make our kinematics charts, one for the vertical direction, which we'll call the y direction for the most part, and one for the horizontal, which we'll call the x. So let's move into our x and y components. Alright, so this is a rehash of what an x and y component is. This was first introduced in forces, but it's the same exact idea for speed or velocity at an angle. When you measure your angle from the horizontal, you're going to have their velocity, so v cosine theta instead of f cosine theta. So say if I have, say 15 meters per second at like 30 degrees, I have 15 cosine theta. Same exact thing for the vertical or the y component. My y component would then be 15 cosine 30 if I had, say, 15 meters per second at 30 degrees. So whenever you have a speed at an angle, you're going to break it up into its components, much like a force at an angle. So let's get right into our examples. So example number 1 that we have here, again, the examples are going to be in the description down below, linked as a Google Doc. This one, we have a ball kicked horizontally with a speed v naught from the top of a cliff of height h. As shown in the diagram below, you have the guy that's kicking the ball off the cliff. So with this situation, I'm not going to give numbers for this. This is going to be one of those derived and expression ideas that is going to be on the part 2 of the AP exam. Kind of want to start getting into that and not worry about numbers as much. There'll be numbers in the second example, which is at an angle example. This one is a horizontal projectile. At first, all we're going to do is just draw our free body diagram. So again, free body diagram is whether forces are acting on the object. All forces are contact forces besides the force of gravity or the force of Earth on the object. When the ball is in the air, there's nothing in contact with it. So that means the only force that I should have on the ball is going to be Fg. And again, that's going to be straight down, because last time I checked, if I drop something, it's going to fall straight downwards. And again, Fg is going to be the force of Earth on the ball. And that should be it. Because when the ball is in the air, so think about a baseball off a bat is traveling, say, over the fence or just in the air for a pop fly. There's nothing else touching it besides, well, there's nothing touching it at all, actually. All you have is the force of Earth on the object or the ball in this situation. So now when we kind of think about how we have zero acceleration in the horizontal direction, the reason for that is there's no unbalanced force in that direction. You can see there's no forces in the horizontal, there's only a force straight downwards, so that's why my acceleration is going to be always downwards when I have something in free fall or a projectile. So this is all based on forces, so that should make a little bit more sense now when we think about acceleration due to gravity, the 10 meters per second being downwards. That's because my Fg is also downwards. My imbalanced force is in the direction of acceleration. So let's move into part B. So in part B, we're going to derive an expression to solve for the time it will take for the ball to hit the ground. Your final equation should only contain given variables and physical constants. So my given variables are the initial speed v naught and my height h. So what we're going to do with this is very much like a regular question where I'm given numbers, is I'm going to do all the algebra first and then plug in my given variables at the end and also my constants at the end. So a constant in this situation, since we're in free fall, we know acceleration due to gravity is 10 meters per second that's going to become g. It's the same exact thing as when we do the weight of an object. G is 10 newtons per kilogram. Same exact units with meters per second squared or meters per second per second. We're just going to make that acceleration g. And I'll show that in a second. But what I'm going to do first to tackle this is set up my kinematics charts. And when I set this up, I'm going to have my x and my y, my horizontal and my vertical. So what I'm going to do here, on the side, I'm going to set up x. And we're going to have here v naught equals vf equals acceleration equals delta x equals, and then time equals. We're going to do the same exact thing for the y direction, which is the vertical direction. And you can use delta y if you'd like to in the y direction. You don't need to. It's the same exact thing. We're just looking at displacement for that. So in my setup here, what do I have based on the horizontal, which is the x direction, and what do I have based on my vertical, which is the y direction? So the y direction, last time I checked, like y based on my axis, y is the vertical. So height should be a vertical quantity. So we can make downwards positive. So we're going to say that the delta x, or the displacement in the y direction, is h. Then, like I said, acceleration in the y direction is 10 meters per second That's the same exact thing as g. So just going to plug in g for that. V naught. So initially in the vertical direction, there is not going to be any velocity because all my velocity is going to be in the horizontal when I start off. So there's not going to be any velocity in the y direction or the vertical direction when I first kick the ball, just like dropping something in free fall. So my v naught is going to be 0, or 0 meters per second, you can say. Vf, not really going to matter as much for the moment. And that's all we should have right now in the y direction. So if you look in the y direction, we have 3 of the variables. We need 3 out of the 5 variables in order to get the time, or in order to get one of the things that we're looking for, either the velocity or final velocity or the time here. We're looking for time, so we have enough there. Let's just quickly look at the x direction, or the horizontal. So the horizontal direction here, which is the x, just for simplification here, v naught, we're given that initial horizontal speed as v naught, so that's why I would plug in for that. Vf, we're not going to worry about for right now. It's actually going to be the same because our acceleration is 0 meters per second squared, or 0 meters per second each second. Again, there's no force in that direction. That's why we have no acceleration. Delta x, we do not know quite yet. We haven't really solved for that. And time, we do not have either. So we don't have enough in the x direction to find time. That's all I wanted to check for there. We do have enough in the y direction. We have the initial velocity, we have the acceleration, we have the displacement, and we are looking for time. So which equation is that going to be? That's going to be my displacement equation. So that's going to be delta x, or you can have delta y if you'd like, equals v naught times t plus 1/2 a t squared. And again, you're going to treat this like if you had numbers. So we're going to do all the algebra first, then plug in the variables at the very end that we've been given. The only thing we're going to do here first is that I know that my initial velocity in the y direction is 0. So I can cancel v naught times t out because anything times 0 is 0. So I'm really left with delta x is equal to 1/2 at squared. From here is just algebra. So I want to solve or isolate t on one side of the equation. What's attached to t right now is a and 1/2. So the first thing I'm going to do here is multiply 2 on both sides of the equation because I'm essentially dividing by 2 on the right side. So over here, we're going to cancel this out. And I'm going to be left with 2 times delta x is equal to a t squared. Then we have a attached to t by multiplication, so we'll do the opposite and divide my acceleration out from both sides of the equation. So I have 2 delta x over a equals t squared. Then the last step here, I have a squared value, so the opposite of that is taking the square root of both sides. And that's what I'll do here in order to get the time. So my final time here, or my final expression here for time, is going to be 2 delta x over a equals t. So now this is where we're going to plug in our variables as if they were the numbers. And then you don't have to even worry about plugging stuff into the calculator and making a mistake with that. So with this, I'm going to plug in what I've been given. So I've been given here h as my displacement. So I can plug in here. I have here 2 times h. I know that a, when I'm in free fall, is 10 meters per second per second. That's also known as g. So I can put in g for that. And that's going to be equal to time. And that's going to be it for that. So it's just going to be 2 times h over g. The square root of 2 times h over g is equal to time. And that's my expression. If I was given numbers, which you're not going to be given numbers on the part 2 of the AP exam, but I just plug in the numbers. It's the same exact idea as plugging in numbers when I'm given these variables. As you can see, I do the algebra first, then I plug in the variables at the very end, and I end up with the answer that I'm looking for. So now let's move into part C. Alright, so now in part C, we're going to use the expression derived for time in part B to solve for the horizontal distance x naught the ball will travel. Alright, so again, we're going to contain only given variables and physical constants. So same exact idea as we did in part B. Now working with this derived and expression idea instead of plugging in numbers all the time. So again, I'm just going to make my kinematics chart here. So again, the x direction is the horizontal direction, and then the y direction is the vertical. So we have here v naught equals vf equals acceleration equals delta x equals, and then time equals on both sides of the both directions. So both the x and the y here. All right. So what we have here, again, same exact idea as we just did. We know that my initial velocity in the y direction is 0 meters per second. We know that my acceleration in terms of variables and physical constants is just g. Delta x in the y direction was h. Time we just found to be as the square root of 2 times h all over g. So that square root is for everything there, just to be a little more clear with that. And now on the x side, we know the initial velocity there is v naught. Vf is not really important, but it's the same exact thing because our acceleration is 0 meters per second squared, or 0 meters per second per second. Our delta x is what we are looking for, and the time in both the x and the y directions is the only variable that is shared between the both of them. So we have the same time here. 2 times h all over g. All right, so now in the x direction, since we are trying to solve for the horizontal distance, we're going to use our kinematics equations for that. So we're trying to find delta x. That's my question mark here. I have initial velocity, I have acceleration, and I have time. So we're going to actually use the same exact equation, which is the displacement equation. So we have here delta x equals v naught times t plus 1/2 at squared. The difference between this version of the equation, or this situation, and part B is that my acceleration is going to be 0. So now the plus 1/2 at squared part of the equation will all be canceled out. Because again, anything times 0, which in this situation is the a, will be 0. Everything on that side of the equation is being multiplied by that a, so this all goes away. And I'm really just left with delta x equals v naught times t. And now this becomes a very simple just plug in based on what we have. V naught actually stays the same here. Delta x, which is going to be x naught in a second, that is equal to v naught, our given initial velocity here. And we're going to plug in what we found for time in the previous situation. So we have here the square root of 2 times h all over g. That's going to be my time. That's where it gets a little bit tricky because you're so used to plugging in numbers for this. There's no number for this, but if you were just given the numbers, you'd be able to go straight away into getting the horizontal distance based on this expression. Say if you were working with Excel or something like that, you could code it to get the horizontal distance for a bunch of different heights or a bunch of different initial velocities and things like that. So now, all I'm going to do with this is the one last part here. They said that delta x is going to be x naught, and that's going to be then v naught times 2 times h all over g. And if you're wondering why I picked x naught or why we were given x naught for the horizontal distance, that was actually a horizontal distance, or solve for the horizontal distance on an AP exam a couple years ago, but it also involved energy in order to get the initial velocity. So x naught doesn't mean the initial position, it's just right now. That's what they called our horizontal displacement. Same exact idea as delta x. It's just sometimes they'll give you this. That's why you have to plug it in there at the end to get the full answer. They've given me v naught as the initial velocity, h as that height, and I know g is that 10 meters per second. So that's what you would get for full credit since they gave you x naught as the horizontal distance there. So that's the full answer. There's a little bit with derive and expression there. So again, it's the same exact idea as what we've done before, doing all the algebra first, and instead of plugging in numbers at the end, you just plug in the variables that they give you, and that gives you full credit if this was an AP exam question. So let's move into part D. Looking at part D now. Now the ball is kicked with double the speed horizontally from the same height. How does this affect the horizontal distance x naught the ball travels? Indicate your answer down below, then justify. So again, whenever you get any of these checkoff style questions on the AP exam, it's always best to justify your answer first, or what is exactly is happening, and then check off, because they could have in the scoring guidelines that if your checkoff is incorrect, they don't even look at how you explained everything on that. But that's not always a guarantee either. So this is one of those qualitative-quantitative translations. You start off with the quantitative part first, the math, and then you're going to explain the math, or explain what's happening based on the equation you created. It could be the other way around, where they could give you something like this to explain what could happen if this occurs, and then you create the equation, and then you'll say, did my equation match what I was talking about? And then you'll get a checkoff type question. But with these, again, explain it first, then make the checkoff. So when I have something that I'm kind of looking at an equation I've created, I'm going to say first is that I'm going to base this on the expression or the equation I have created. So that's where I'm going to start off here. So we base our response on the expression for horizontal distance derived in part C, which was x naught equals v naught times the square root of 2h over g. Okay, so now looking at this, time, which the time is going to be controlled by the height, because the only thing that's going to change in the expression for time is height, because we're not going to leave Earth. So if we increase the height, we're then going to increase the time of flight. If we decrease the height, we are going to decrease the time of flight. Since the height is the same, we can say that that's not going to change. So that's not going to change our horizontal displacement at the moment. So that's kind of what I said here. The height of the ball is kicked from remains the same. So in turn, the time of flight also remains the same. The rest of that equation is constants. The 2 is a constant, and g is a constant on Earth. So again, only thing I can change there is my height. In order to change my time, that's not changing, so the time is the same. So now we can talk about what actually is going to change. So what actually is changing is my initial velocity. So I can talk about that my initial velocity is going to double. So if I can change my horizontal distance traveled would now be just changing the initial speed the ball is kicked with. Again, since my height doesn't change, my time doesn't change. So that's the thing that doesn't change. That's what I'll explain first. Then I'm going to explain what does change, which is my initial speed. Since this initial speed is going to double, while the time ends up remaining the same, that means that I essentially have 2 times 1 if I was doing, say, a factor of change. So my horizontal distance should also then double. So that's what I'm going to end up checking off here. And the distance the ball travels in the horizontal should double. So there we go. So that's our full explanation, kind of a short paragraph response based on everything that I've done here. Again, we talk about the equation that we've created first, or the expression, talk about what stays the same, then talk about what is going to change and how it will end up changing the situation described. So let's move into example number 2. All right, so example number 2, this one's going to be a launch projectile. We're going to start off again with our free body diagram. So the situation as described is a pumpkin is launched from ground level at an angle of 60 degrees to the horizontal with an initial speed of 30 meters per second. The pumpkin hits the ground at the same level it was launched at. So that's going to be important for our final velocity of the pumpkin. Again, these examples in the description down below. Just go right to the beginning there, and they should be linked for the examples and the full facts that I'm taking my explanations from. So what we have here, draw on the free body diagram of the pumpkin. Ignore air resistance again. So when the pumpkin is in the air, nothing else is touching it. All forces besides the force of Earth on an object are contact forces. So that means all we're going to have here is Fg. And last time I checked, when I drop something, is going to fall straight downwards. And again, Fg is going to be the force of the Earth on the object, which in this situation is going to be the pumpkin. So that's it. The force of the Earth on the pumpkin, there's nothing in contact with it where it's in the air. So all I have is my non-contact force, which is Fg. So let's move into part B. So let's look at part B here. What is the direction of the pumpkin's acceleration? So for this, I'm going to kind of go off my free body diagram. So I'm just going to draw it over here. And I know the only force that I had present on the pumpkin while I was in the air was Fg, and that is straight downwards. So there is a fact straight from my fact sheet for forces that talks about unbalanced forces. So give yourself a second to go to dynamics, or pause the video, and look for Newton's second law, and that will talk about unbalanced forces, because that's what I'm going to end up using to explain this situation and the acceleration that I have here for this projectile. All right, so I'm going to explain this now. So if you haven't found it yet, just pause the video. So my initial fact that I'm going to use here, my evidence for this situation, is going to end up coming again from Newton's second law, and it's going to say here that an object's acceleration is in the direction in which forces are unbalanced. All right, so that's going to be my evidence for this situation here when I do my ERC. So then my reasoning is going to be that since the unbalanced force is directed downwards, since the pumpkin's forces are unbalanced downwards, whatever you want to say with that, since the pumpkin's forces are unbalanced directly downwards, that is going to be my reasoning. My claim is then going to be my answer. That means that my unbalanced force is downwards, acceleration is in the direction of the unbalanced forces. So my unbalanced force, or my acceleration should also be directly downwards. And this should make sense here because my only acceleration, I have no acceleration in the horizontal direction. My acceleration is going to be straight downwards, that 10 meters per second. That is going to end up being my claim. So that's going to be important when we talk about the horizontal direction and the vertical direction in a second. So let's move into part C. All right, so take a look at part C. How long was the pumpkin in the air for before it hit the ground? So whenever we have a projectile question, we're going to make our kinematics charts for both the x and the y direction, otherwise known as the horizontal and the vertical directions. So let's see here. We have the x direction, then we are going to have the y direction over here. So we're going to have v naught, vf, acceleration, the displacement, and my time for both the x and the y direction. All right, so now we're just going to plug in for what we have on both sides here and then look for an equation that is relevant to this. So in the x direction, we are going to use our initial velocity. We have a velocity at an angle, so we're going to end up breaking this up into our x and y components. So that is straight from the dynamics fact sheet. I also have it at the beginning of this video. For anything that is measured from the horizontal, we are going to use here for the x or the horizontal component cosine. So for this one, we have here my initial velocity, which is 30 meters per second. And we're going to multiply it by cosine of the angle here, which is 60 degrees. All right, so then we have here my final velocity. That's not going to be very important. It is going to actually be the same exact thing. Why is it the same exact thing? We have no acceleration in the horizontal direction. That is, again, due to the fact of the matter that we have no force in that direction, so we have no acceleration. So this acceleration, again, is 0 meters per second, or just 0. For the rest of the x, we don't really have anything for it. We don't have the delta x, we don't have the time. So now we're going to move into the y direction. So for the y, if we use cosine for the initial velocity in the x, we're going to use sine for the initial velocity in the y direction. So we're going to have here 30 meters per second. That's times sine of 60 degrees. Vf, whenever I throw something upwards or launch something upwards, if it comes back to the same position that it was thrown from, it's going to have the same exact speed, but the opposite direction. So in other words, it's going to have the negative velocity or the opposite sign velocity that it had originally. So if this is going to be positive 30 meters per second times sine of 60, my final velocity is going to be negative 30 meters per second times sine of 60 degrees. All right, then my acceleration. I know my acceleration is downwards. We figured that out earlier. So that means it's going to end up being negative here. And then my acceleration, the actual number or the magnitude of the acceleration in the vertical direction, that's going to be our 10 meters per second delta x is actually going to end up being 0 for the full flight because it comes back to the original position that it was at. So my actual vertical displacement is going to be 0 meters. And then my time is my question mark. That is what I am looking for. So we do have enough in the y direction in order to find the time. You don't want to use the displacement equation though. Even though you have the displacement, it ends at the same height that I started off at, because you're going to end up having to do a quadratic. It's going to be really messy. Don't do that. There's a much easier equation. We have the initial velocity, we have the final velocity, we have the acceleration, and we're looking for time. That's going to actually lead me to my final velocity equation. So again, those equations are on the reference table or they're in the fact sheet for kinematics. So Vf equals V naught plus AT. So now we're going to start plugging in what we have here just based on variables. So my final velocity there is going to be the negative of my initial velocity times sine of theta. That is then equal to my initial velocity here, v naught, times sine theta. Let me fix that, it's really sloppy. And then what we have here is plus, and since my acceleration is negative, I'm going to give this a negative a times t. So our whole goal here is to get t by itself on one side of the equation. What we're going to do here first is, since v naught times sine theta is attached to negative a times t by addition, we're going to subtract this on both sides of the equation. So that's going to cancel out over here. I'm going to end up being left with, on the left side, negative 2 times v naught sine theta is equal to negative a times t. So the last step here is, in order to get t by itself, it's being multiplied to negative a. So divide out the acceleration from both sides of the equation. So I should be left with here negative 2, or you can really, now it's a negative over a negative. So we're just going to have here 2 times v naught sine theta all over a is equal to t. And again, the reason why I got rid of negative, I have negative over a negative, that's a positive. So now let's just plug in our numbers, and we'll put this off to the side here. So I'm going to have here 2 times v naught, that was my 30 meters per second, times sine of 60 degrees. That is then going to be all over 10 meters per second. That is equal to t. You're just going to plug this into your calculator, and you're going to end up with the answer here. So 30 sine 60, that is going to end up being 25.98. Multiply that by 2, you're going to end up with around 52 or 51.96. Divide that by 10, and you're going to end up with your final answer there. That is going to end up being about 5.2 seconds. So my time here is going to be 5.2 seconds. You can put that up there for both the times, and we will on the next part of the example. So let's move into part D. The last part of this example and of the video, how far did the pumpkin travel during this time frame? So this means the horizontal distance that the pumpkin travels. So we're going to really be just working in the x direction. I'm just going to write out everything that I've had here in the x and the y. So we have here, again, the x, which is the horizontal direction. And then I'm going to have there the y, which is the vertical direction. So I'm going to have here v naught, vf, not v there, acceleration, delta x, and then my time. And then in the y direction, I'll have the same exact thing. I'm not going to need this as much because we're working in the horizontal mostly. I just want to know what my time was and bring it over to the horizontal direction. Starting off here at my initial velocity. Again, since we have something at an angle, we can use our x and y components here. So in the x, we have 30 meters per second, and that is cosine of 60 degrees. Then in the y direction, we have the same exact thing, 30 meters per second, and that is going to be sine of 60 degrees. Oops, I'm just going to put that on the outside. All right, then we are going to have here my final velocity. Final velocity in the x direction is the same exact thing. No need to write it there twice. In the y direction, we had this as then negative 30 meters per second times sine of 60 degrees. My acceleration in both the x and the y. My acceleration in the x, that's going to be 0 or 0 meters per second because there's no force in that direction. In the y direction for this situation, we had the downward as negative, so it's just negative 10 meters per second per second. Then my displacement, we do not know that in either direction at this point. Really for the y, if we're going for the full thing, it's going to be 0 since we are going to the same level we will launch that, though it's not really going to end up mattering. And then my time, we were able to then find out as 5.2 seconds. All right, so the time in both the x and the y direction are going to be the same exact thing. So we have here that time is 5.2 seconds. So then we can end up figuring out what the displacement is going to be in the x direction. We have enough here to now find it out. We have 3 different variables and we have one that we are missing. So let's look at the equations to see which one we're going to use. And this is going to be the displacement equation. So displacement in the x direction is going to equal v naught times t plus 1/2 at squared. Again here, my 1/2 at squared, I have acceleration as 0, so anything multiplied by 0 is going to end up being 0. So this whole term is going to cancel out. So I'm left with delta x is equal to v naught times t. So now I'm just going to plug in what I've been given because I want to have here delta x. So one last thing here. V naught in the x direction is v naught times cosine theta, and then that is times time. So now I'm going to plug in what I have here. Delta x is equal to v naught, which is 30 meters per second, times cosine of 60 degrees. That is then multiplied by 5.2 seconds. We are then just going to plug this all into our calculator and end up with our final answer here. So 30 cosine 60 is going to be 15. That is times 5.2, and that will give us 78 meters. So our horizontal distance there is going to be 78 meters. Again, for this, actually, when you do this, the time, you would solve for the time. If it was like a 2-part question, you'd solve for the time in variables first and actually plug that in as whatever I would have gotten in the previous question, where I believe time was like negative 2 sine theta over negative a. You'd plug that actually in for time if this was a full-on AP question. But I just want to get down the fundamentals of launch projectiles. So I hope these examples were helpful, and see you guys in class.